Hey guys, I thought I'd give you a couple of examples of actually using those time-dependent equations for an RC circuit. One where we're charging a capacitor, and I'll also do one where we're discharging a capacitor. As you can see, I've got number 38 queued up on the screen. This is from your textbook. It's on page 862. So if you find number 38, you can follow along in the book, but there's the text right there for you. I made a little video of me working it out, which I'll put on the screen and we'll pause periodically. But the equations that I'm going to refer back to are the ones that I gave you in class and told you to take a picture of. Now, if you weren't here, most of the ones you need are up on the screen up above. So just defining our terms, if you see the EMF symbol there, right, the funky E, that's the volts on the battery. The C is the capacitance, and then of course R that you see down here is the resistance, okay, of the resistor. All right, let's start that video. Now, if you watch, you're going to see that I'm using the tau equals RC from up here. And of course, the resistance and capacitance are given in the prompt. They're in not great units, so you do have to convert, right? You can see I took the mega ohms and put them in regular ohms, and the microfarads and put them into regular farads. Now, the time constant, I'm going to pause this in a moment. The time constant, RC, relates to the rate at which the capacitor charges. So a big time constant means it's a slow charging capacitor. A small time constant would mean the reverse, and it does have units of seconds. You can memorize that, but if you're curious as to how the crap RC works out to be seconds, then take a minute and look through the derivation I gave right there for how exactly that comes out to seconds, because it's kind of neat how that works. All right, let's keep going. Part B of the question is going to ask about the maximum charge on the capacitor. What I want you to notice is I'm not actually going to use the equation from up above. Or I am, sort of. I'm just going to use a very small part of it. Most of it isn't actually going to matter. And there it is. So if you notice, the only bit that actually got used was EMFC. That's because it said maximum charge. If it had said, what is the charge at some particular time, which the problems I assigned might actually do, the charge at some particular time could be found by using that equation, which is this one right here, right? And then I write it EMFC, CMF, same thing. If you actually, say, plug in a particular time and, you know, everything else, then that'll actually spit out then what the charge is at that particular moment. If all you care about though is the maximum, then you don't need to plug in anything except EMF and C. Now the next part of the question is going to ask for the current at 10 seconds after the switch is closed. So in a related vein, if they had said simply, what's the maximum current? You wouldn't have to do very much math at all. You certainly wouldn't have to use the E stuff. You would just have that right there. So for all of these equations with time in them, the maximum is always the thing out front. So there's your maximum current, there's your maximum charge. That's how it's always going to go. All right, now it did ask for the current at some particular time, so let's see how this goes. I'm going to be using that equation I wrote up top. I'm not sure why they use a lowercase I for current, but there it is. Reminder, we're plugging in 5 for RC, because that's what we got above. Okay, and there it is. So plugging in 10 seconds for the time, 5 seconds for the time constant, and then the values of EMF and R, we end up with 4.06 microamps, which is really not an awful lot. All right, I'm going to do an example of discharging next, which is going to be like number 39. So stay tuned for that.